Did you get your tickets to the gun show? Don't worry, because they're free. Oh yeah. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive project this week. I'm going to finish the sheet metal work for the tender water tank. There's some pretty challenging stuff in here. Sheet metal work, not my forte, but let's see how we get along. Let's go. Quick update before we get started. This is me and my dad at the local model engineering club having just passed pressure testing on my boiler. So those of you who've been following this from the beginning, you might have wondered, hey, did that boiler ever pass certification? Yes, it did.
Utility boiler, so
yeah.
when we did a hydro and it didn't work, you knew you were in big trouble.
Yeah.
That looks really good.
Yeah.
No sign of any water.
Nothing.
It would have come out by now. What have we got?
So someday when this locomotive is finished, I will actually be able to run it at the local track, which I'm very, very excited about. Okay, on with the show. When last we left our tender, it looked quite a bit like this. You can see I've got the sides and the coal bunker in place. Now it's time to fill in all the spaces in between with sheet metal, starting with these front panels, which are gonna be tricky. I want to start by laying out the edges of the panels where they need to land. I've learned the hard way with sheet metal work that you want to have consistent references to start with, so that as you're doing all of your bending and filing and test fitting and so on, you're always coming back to the same place on each test fit. Then I used a fabric tape to get an approximate length, and I'm going to make a paper template for these pieces because they are so tricky. There's a lot of shape and form to them that has to land in exactly the right place, and I don't trust my ability to do that straight from the drawings. These pieces need to be kind of scribed and shaped around the edge of the verge board, that little trim piece that runs around the front edge. I need to make a little hole for that. With that established, it became clear that the sides of my coal bunker are not as straight and square as I thought they were. You can see I've got kind of an angle. The coal bunker seems to be a little wide at the front. I thought I checked all that, but, well, it's not as square as I thought, and that's why I'm glad I didn't do this straight to sheet metal. I'll add a little filler piece to get the angle that I need to create in this area so I can get that to fit properly. And I think I'm ready to transfer now to sheet metal. I tape this part down to the brass, and I'll scribe the outline of it carefully with my scriber. That technique of using small filler pieces to establish the outer vertices of a complex shape is actually something I learned from Tally-Ho. You never know where knowledge is going to come from. A technique used in wooden shipbuilding turned out to be just the thing for solving this little scribing problem. Next, I'll rough cut out this piece on the bandsaw. Of course, you've seen me do lots and lots of this. I'm staying pretty clear of my scribe lines because I'm going to be going down to the scribe lines with more precise techniques, as you'll see. The other side is a mirror image of this piece, so the first thing I tried was flipping my template over and fitting it. Maybe I'll get lucky and it'll fit, but I don't really expect it to. And well, it's actually pretty close. I need to extend the length a little bit at the bottom, and the angle on this side was slightly different, so I needed to shift some of my filler pieces around a little bit. But actually not bad. I was able to modify that template to get the other piece. Next, I set up the first piece in the milling machine. Even though the coal bunker itself is not super square or straight, there are two sides of each of these pieces that are perfectly straight and parallel. That's the main outer edge and the inner edge up to where the coal bunker meets it. So those I can do on the milling machine, and I'll have at least some consistent straight references to use, which will be really helpful. I clamped the pieces to a parallel for extra rigidity. When you're end milling the edge of sheet metal like that, it's very easy for the end mill to grab that sheet metal and bend it. But that little parallel sandwich did a nice job of preventing that. That's something that I've had happen in the past, so I'm wary of it. For the area that needs to fit around the coal bunker, I went to the die filer. It's kind of at a funny angle, and it wasn't going to be easy to create this edge on the milling machine, so I'm just die filing down to the scribe lines. Then for that little notch that goes around the verge board trim, I used some needle files. I'm going down to my scribe lines, which should be really close, but I'm expecting to need to do some fitting. And boy did I ever. This was back and forth with test fitting and filing and test fitting and filing for probably a few hours to get both pieces done. The trick was the fit had to be perfect, or as close to perfect as I could get it, but also these pieces need to be sitting in just the right place and at just the right angle such that they will meet up with the big plate behind them, and they're going to be straight after the front edges are bent downwards. So if these pieces aren't sitting perfectly straight and parallel and at the right width in this position, then when I bend them, they're not going to be straight down the front, and the back edges aren't going to line up with the edges of the large back plate. So this was really worth taking my time because these front pieces are going to dictate the fit and finish of everything around them. One thing I noticed in this fitting process is that the sides of my coal bunker are not very straight. The top was about 20 thousandths wider than the bottom, which was really making it difficult to get the fit and the parallelism that I wanted out of the front pieces. So to that end, I took the coal bunker off and fixed the straightness of it. I braced the bottom with a machinist jack and just kind of squished it in until it was parallel top to bottom. I couldn't modify the bottom because of course the bolt pattern is there, which is already set, but squishing in the top helped a lot on getting this fit that I wanted. Once the width was what it was supposed to be at multiple points all the way down the lengths of both pieces when sitting in their final positions, then I knew I was there. Here you can see how the two sides of the coal bunker are, in addition to not being straight, not perfectly symmetrical either. A little bit of variation there. That variation is not enough that you can see by eye, but when you're trying to fit pieces extremely close to those surfaces, then those little differences start to matter. I'm going to pause on those now and work on the back piece because I want to bring all three pieces up at the same time to make sure they all stay fitted together as I go along. So once again, starting with a very rough length measurement from the fabric tape, and then I'm going to rough cut a piece of stock oversize, and once again make a paper template for this piece. Again, this seems like a very simple piece, but now that I know that my coal bunker is a random shape and size, I don't want to trust making sheet metal to the drawings and hoping that it'll just fit. So I got a piece of paper that should be a little oversized but close, and I'm getting it centered on the copper sides to make sure it's landed in the right place. Mark my positions so I can get back here for test fitting, get a rough idea of how big the coal bunker is, and mark that out. Now I need to get the radius of those corners. Now again, I know these radii aren't what they're supposed to be according to the drawings precisely, but I also don't have a radius gauge big enough to measure them, so I don't know exactly what these radii are. So instead what I did was copied them with some copper wire, sort of a poor person's French curve, if you will, and then I used that wire to transfer the curves to my template. This actually worked surprisingly well. On the first test fit cutting to those lines, it was almost perfect. Using a French curve like that is not something I've ever tried before, but seemed to work really well. Maybe I should buy some real French curves at some point. I had to go back and forth a couple of times and do a little bit of shaving here and there on the template, but that's why I'm doing this in paper and not metal. Once again, I'm making sure that I'm landing right on those scribe lines where I marked the end of the front edge panels. I got to make sure these panels are going to mate up nicely, and I'm keeping the panels centered left to right on the copper flanges as I go. Now with this piece taped in what should be the final position, I can work on this back curve. I left this over length so I can fold it down, mark with what the length should be, cut that off, and that looks pretty good. It's a little tricky to see, but you can see why I didn't want a chance doing this in sheet metal. It would be very difficult to get this length just right. The floor pan of the tender sticks out past this edge, so you can't just fold the sheet metal over, let it hang down, and then cut it short. There isn't space to do that, so that's where the paper template is a big help. Final confirmation that everything fits nicely with the front panels as well. I think I'm ready for sheet metal on this piece. I've left the sheet metal long at both ends because neither of the ends of this piece are factory or straight cuts, so I don't trust either of the edges as a reference. I'm tracing both edges. However, conveniently this panel is the same width as a piece of factory stock that I was able to buy, so those long side edges are factory edges, and I'm just going to leave those alone. They are fine as they are. They are pinch cuts, so there is some slight distortion in them, but this material is so thin that you really can't see the distortion. And they're not, to be honest, as straight as they would be as if I'd machined them, but they're close enough. Never assume that a factory edge is perfectly machinist straight and square just because a factory did it. I found those long side edges were actually out by about 5 thousandths. So those ends, though, that I rough cut on the bandsaw do need squaring up. Once again, more fitting and filing. The die filer was a big help there. And I did the same process as on the front panels, just constantly checking and test fitting and making sure that I'm landing on my marks with each test fit until I had a good fit and all the panels looked like they're going to line up. And now I can move on. I'm going to go back to the front panels now because I've got the rear at a place where I know everything's going to line up. The next step is to emboss the rivets on these panels. I made this rivet embossing tool. I did an entire video just about this tool if you're interested in more detail, but you'll see how it works here. I start by annealing all the panels. They need to be nice and soft for this process. What I'm doing here is creating a pattern of fake bumps on the panels that makes it look like the riveted panels of the real steam locomotive. I started by making paper templates on my computer with the pattern of rivets that I wanted. The pattern is mostly consistent, but not 100%. As you can see, the spacing is a little different on the sloped sides, and it varies a little bit left to right versus the long way also. And all of that is to ensure that a single rivet lands in each corner, which looks nice, and to make sure that the seams in the panels land exactly halfway between two rivets, so that when panels made up, the rivet pattern looks continuous. I used Affinity Designer for this, which has great tools for this kind of layout process, but you could also use Adobe Illustrator or Inkscape or whatever drawing program you are comfortable with. I'm a big fan of the Affinity products myself. Not sponsored, they're just great pieces of software. Those pieces are then spray glued onto the sheet metal with Super 77. It's a really nice temporary spray glue. I like it a lot. It's messy stuff though, so careful where you spray it. Of note here, these rivet patterns are mirrored because the template has to go on the back because we're embossing the rivets from behind. I almost did that wrong. One of my awesome patrons pointed that out to me, and I quickly ran into the office and flipped those patterns in the software and printed them again. So thank you very much for people who give me little tips like that. Many eyes are better than two, unless all those eyes are on one thing, and then woof, gross. You can see now how this embossing tool works. There's a hardened tool steel pin that presses down into the brass, and underneath that is a hardened steel die which catches the edges and allows the pin to form the rivet head. There's a fence on the tool, and the fence is setting the spacing of the rivets away from the edge of the material. The paper template is just telling me the horizontal spacing of the rivets. I'm not really paying attention to the width. I mean, obviously the fence should be in the right place according to the paper template, but the fence is the final arbiter of distance because that's more likely to be perfectly accurate than the paper template glued onto it is. For the edges that are at funny angles, I had to then retract the fence and do these ones freehand relying on the paper template. Quite a lot of development work actually went into this embossing tool that I'm glossing over. It's why it's getting its own video. The Super 77 spray glue then peels off, and you can clean up any residue with acetone. I did both pieces that way, and here we are now. You might ask why I did the riveting first before doing the bends, which has to come next. This is the way that Kozo says to do it in the book. I think because riveting the bent pieces might be difficult, so that's why he says to do those first. However, that's nerve-wracking because it means the bend, which is the most difficult thing, has to be done last. And the trick with this is getting the bend in exactly the right place. For this, I have a crazy mad scientist idea. What I really need to ensure that bend lands in exactly the right place is a mandrel that sits in situ on the final part, so that the piece is in its final position when I do the bend, thus guaranteeing the bend is in the correct place. What I've done is found a scrap of mild steel, and it has to be mild steel, hence the red markings. It's part of my internal scrap marking system. And I've stuck it in the lathe. I got some tail support in there because the scrap had a narrow end on it, which means it's not a very rigid setup. So the tail support is necessary to turn this down to the final radius that I need for the bend on this piece. And as you can see, mild steel is not very pleasant to turn. I couldn't get it to break a chip with that insert, so I switched to this high-speed steel tool, which still wasn't breaking a chip, but at least the rat's nests were more controllable. Machining 1018 mild steel is never pleasant. It's really not a very good machining steel. But I have to use 1018 and not something like 12L14, which is more what I have around here, for reasons that you'll see momentarily. Ooh, the suspense. Now I decided to part this off. You can see I've got the tailstock in there, which you don't normally want to do when parting, but I'm not going all the way through, so this is safe. It's not safe to have the tailstock in there if you're going all the way through, because the tailstock's putting pressure on it and you'll trap the parting blade. When I got close to the end, I did try taking the tailstock out, but as predicted, the setup is not rigid enough for parting and it was chattering like crazy, so Didn't want to push my luck on shattering a blade, so I'll break those edges now, then take it over to the bandsaw and finish the cut. And Yahtzee. Who says I don't say Yahtzee anymore? Yeah, I read your comments. Now you can see hopefully where this is going. This little mandrel slug thing is going to go right in there. You can see the radius is a perfect match. And that's going to sit in there and be the bending mandrel. I can't rely on the brass and copper on the edges to act as bending mandrels by themselves. A, because the copper is annealed and probably not very sturdy. And B, because if you support it only on the edges, when you do the bend, the material is going to try to take the shortest path. It doesn't want to bend because that bend is a stretching action. And so it's going to tend to buckle in the middle between the supported areas. The next piece of the puzzle is a piece of square bar that I've milled a small clearance on to fit around the edge of the coal bunker. That slides in there like so. And now I've got an adjustable parallel that I'm going to use to measure the gap that needs to exist between these two pieces. You'll see why the long square bar is long in a moment. Now once I've got that height established such that the round piece is sitting at exactly the right height off of the square bar, then I can measure that parallel and I cut a little piece of scrap to that distance. I found this random piece of scrap that I think was a drill guide, and I just machined the ends of it to be the correct length. And that will fit in there like so. And one last check with my bending mandrel that's going to sit on top of that. And there we have it. You can see how this is all going to work. Now, the reason all of this is mild steel and none of it is 12L14, which would have been easier to machine, is because I need to weld all these pieces together. The first couple of tacks failed miserably because my ground sucked, so I fixed that and finished tacking the pieces together. 12L14 or any free machining alloys that have lead in them really don't weld very well, so that's why this all had to be 1018 mild steel. In general, the weldability and machinability of a steel tend to be opposite. The ones that are really good for one tend to be the worst for the other. It's not universally true. There are some alloys that are good at both. I think 4140 is pretty good for both, but it is kind of a rule of thumb with steel alloys that the more machinable something is, the less weldable it tends to be. Now you see how this Frankenstein mandrel contraption is going to work. I slide it in like so, and that's going to hold the mandrel up in space very securely, exactly where it needs to be, square it up with the front edge, and the square bar is long so that I can clamp the tail end of it down here, which is the only accessible area once the bending starts. Then I clamp the rear edges of the material to the flanges on either side in final position, get some wood in there to keep the sides straight as I do this, and away we go. Oh, very tense. No idea if this is going to work or if the bottom edge is going to land in the right place, and I can't adjust it because the rivets have already been done. Whew, wow. I gotta say, that seemed to go super well. Once the bend is started, then I can pull the mandrel out and finish the bending so that it lands perpendicular. Of course, when bending in situ, you can't get a perfect 90-degree angle because of spring back. Even on annealed brass, there's a little bit of spring back. But once the bend is started in the right place, that's the hard part. And look at that. A little fine-tuning yet, but overall, that really, really worked well. It was probably a couple of hours of effort to make that mandrel and figure out how to do this, but I mean, at this point, I've got probably 40 hours of work into these front pieces, so an extra couple of hours to make sure that I didn't scrap it by doing that bend wrong was well worth it. That single bend was one of the most nerve-wracking ones on the entire project so far. There was just no margin for error there. That had to go perfectly. Now you might be asking, why am I drilling out some of my rivets? So Kozo's design here, which I think is pretty clever, is that these rivets are sized to be basically to scale, but also the same size as the heads of number 0 screws. Because like any other complex soldering operation, you have to hold all the pieces together with fixturing screws during soldering so nothing moves. So one by one, rivets were drilled out, then holes were lined up and matching threaded holes were drilled on the mating pieces until everything was bolted together in its final resting position. Next up is the bend for the large back piece. This I'm going to mark and do on my press brake. It's just a simple straight bend, so I don't think I need any tricky in-situ mandrel like I did before. I think I trust myself to get this in the right place. The line needed to be transferred to the other side because the line that I could mark is the opposite of where the bend needs to be. But since those front edges are machined parallel references, it was a simple matter of using odd leg calipers to transfer that line to the other side. I'll check the angle that I need to create with a protractor. I'll capture it and save that and bring it over to the press brake so I can make sure that I copy that angle. And away we go. Line that up carefully with my scribe line. At this point you might be thinking, hey Quinn, I'm into PPE as much as the next person, but a respirator for a press break seems like overkill. And you are correct, unless you've spent the whole morning doing torch work in your shop and it's freezing outside, so the doors are all closed, so it's kind of smoky in here. All right, that felt about right. Let's see how I'm doing with the protractor. Probably need to adjust this a little bit, and oh my gosh, got it in one like a boss. That might be the first time that's ever happened in my history of press brake use. Test fit on the assembly now, and boy, look at that. What a nice fit that is. That really could not have gone better. With that bend in place, now I can lay out some features that we need to create on this sheet. There's a large square hole for the main water hatch, and then there's a bolt pattern behind that. And they are laid out relative to the bend. So we had to do the bend first, and now I can cut these out. The book says to do this with a fret saw and a file, but I just put it in the mill and milled it out. That seemed easier. And because I've got it all set up with the DRO as reference from that bend line, I can also just jump over and do the bolt pattern. The bolt pattern holds a large work light that sits on the sloped back of the tender. Next, there's an elaborate rivet pattern that goes on this back piece. I waited until after that first bend to do the rivet pattern as well, because I wanted to do the rivet pattern in 2 sections. Again, to make sure that I can massage the spacing of the rivets so that it looks like the same rivet pattern everywhere, but I make sure that that bend in the panel lands exactly halfway between 2 rivets. I think there's really no way to guarantee that happens except doing the bend first and then doing the layout in software of the rivets after that. And I used 2 separate templates for each of the 2 sections. I'm really glad I did it this way. This made it really easy to ensure that the rivet pattern was perfect. Then back to the rivet machine to emboss those. You might be wondering why not have a registration hole on the die so that you can line up the previous rivet with the current one and thus keep the spacing consistent that way instead of doing this paper template. The problem with that is that error is then cumulative. If you don't seat one rivet perfectly in your registration, then every rivet after that is off. Whereas with a global pattern like this, error is all kept local. If any one rivet is off a little bit, it doesn't affect any other rivets. Plus the rivet spacing is actually subtly different on each edge to make sure that, again, rivets land in the corners nicely and that the spacing is all even, but the pattern density looks to the eye the same everywhere. There's very subtle spacing differences all over the place to make all of that happen. One last very tricky bend. The rear edge now needs to be curved down around. I would have liked to have used an in situ mandrel again for this, but there wasn't space in there. I would have had to create some crazy like half circle thing, and there isn't really room to do the forming by hand the way I did before. So I thought this would be easier. Using a mandrel from the scrap bin that's the correct size, and I've marked where the bend needs to start. This is the Kozo suggested method for doing this bend. The softwood on the vise protects the rivets, and then you use a piece of hardwood to bend the piece over around that mandrel. Now this was working, except that I could see that the bend was going to end up in the incorrect place if I continued. So I stopped here and I switched methods. I think this works for Kozo because he has a little bit more of a straight edge at the bottom of his curve than I do. On my tender, for whatever reason, the curve kind of runs straight down into the bottom. So I decided I needed to finish this with hammer forming to make sure the curve went right to the very edge of the material. Now I knew I was potentially going to smash my rivets doing this, but I figured it wasn't going to be a big deal to re-emboss them afterwards if necessary. But actually, honestly, they stood up just fine. I think the rivets themselves are all work hardened from the embossing process, and the soft-faced hammer honestly didn't seem to bother them at all. If I was going to do this again, I think I would do the rivet embossing last. The book says to do it all first for the reasons that I described earlier, but I honestly don't think it's really helpful. I think it's lower risk to do them last once you've got the sheet metal fitting. I did, however, manage to get what I think is a good fit. That seemed to go really well. I was pretty nervous about that little curve at the end as well, but that seemed to go just fine with that hammer forming, so chalk one up for beginner's luck, I guess. I made a little cross member off camera to fit in the bottom, and now, once again, many tiny fixturing screws to hold all of this together. There's something like 30 of these number 0 screws that hold this entire assembly together, and each one of them is quite a bit of work. You got to drill a couple of clearance holes, transfer those into the mating flange, take the mating piece off of the base plate, take it over to the mill, drill and tap that mating hole, put it all back together, mark the next couple, and so on. Quite a bit of work, but when you're done, you should be able to remove the entire assembly off the base plate and it should hold itself together with the sheet metal tying everything together, which for me almost worked. I knew these corners were going to be trouble because my copper flanges are a little too short, which I also knew, so I wasn't able to get fixturing screws in those flanges on that edge, so there was nothing holding those corners together. So I made some little scrap plates to fixture them together for soldering. I transferred the holes from the base plate and used that to hold everything together in such a way that I can still get solder into those joints. That seemed to work fine. Then everything comes apart again. I got to clean all the Sharpie mark off of everything because Sharpie does not get removed by pickling acid, one of the great cruelties of the universe. Everything gets pickled and then reassembled with flux this time on all of the mating surfaces. The base plate is acting as an assembly fixture here. It's not actually going to get soldered at this stage. Well, it's actually never going to get soldered. There will be a gasket underneath this entire assembly eventually, so that the tank can still be removed for service. And then away we go. I've got a small tip on my torch this time. This is a propane torch. This is just soft solder, so this is plenty of heat for this process. And away we go. This seemed to be going okay. Some of my joint clearances are better than others, and I know that, but I felt that everything was close enough that I could get away with it with soft solder. We'll see. This is a lot of joints and a lot of length, so plenty of places for things to go wrong. Luckily, soft soldering is pretty easy and way more forgiving than silver solder. So if you make mistakes, you can come back and tune things up, reflow the solder. It's all pretty easy, relatively speaking. That's not to say I'm good at this or that I will necessarily do a great job here. After pickling and cleanup, here is the tank so far. At a glance, it seemed to go pretty well. It's certainly very strong. The solder structurally did its job. Areas like this where the joint clearance was tight came out great. Areas like this where the joint was a little too loose were not as great. And then I had a few spots like this where the joint clearance was clearly really not good and solder really blobbed out. And I had a tough spot here where the solder blobbed out around the trim board. That's going to be a little tricky, but I think we can clean that up. The biggest issue I had was these outside edges of these front panels. Because I didn't have fixturing screws in this area, because of the flanges being too short, the brass expanded more than the copper did, and these gaps opened up. So I learned a valuable lesson about what fixturing screws do in an assembly like this. They don't just hold the pieces in position, they also keep the joint clearances tight if the metal expands or warps. On the other side, the same thing happened, but the solder flowed through and made a big messy blob that I'm going to have to clean up. I'll start with this tricky area inside the verge board. I'm going to use a couple of techniques to clean this up. First, to get rid of the bulk of that excess solder, I'm going to use my desoldering vacuum gun, or moo gun as a viewer called it. I love that. And then I'm going to use the wet rag trick. This is a technique that a bunch of commenters taught me in a previous video. Just wipe it with a wet rag while the solder is hot, and you can wipe away basically all of the solder. You still leave like a 1-molecule film of solder, but this is all going to be painted, so that won't be visible in the end. That wet rag trick is super good, so thank you to the people that gave me that tip. I used that same thing on all these other big blobs, and boy, really works well. It really cleans up the joints and makes them nice and gets rid of all the excess solder. I did also do some filing in a few places, both to get rid of excess solder and clean up some of my joints a little bit. It would have been amazing if, after all that, all 18 holes in the base plate still lined up, but they didn't quite. I had to do a little filing on a couple of these clearance holes to make everything fit, but I think almost all of them still lined up, which is kind of amazing. A little bit of luck there, I think. The entire assembly will need a little bit of flattening on the bottom. It's almost flat, but there is a slight warp to the entire structure. I thought bolting it to the heavy brass base plate might actually take the twist out, but the structure is now stronger than the base plate is, so it's actually twisting the base plate a little bit. But it's close enough for now, and I'll clean that up a little bit before I put the final gasket on underneath. Let's get this in place now and get a sense of what our tender is going to look like. It's really looking like a tender now. A few people asked why the tender is this shape. Like, wouldn't it hold more water if it was a box? And yes, it would. This is called a slope back tender, and it was used on switchers because it gave the operators a better view of the rear coupler. Switchers spend their whole lives in yards, they're never that far from water, so they don't need as much water capacity, and the slope back tender giving better coupler visibility was a good trade-off. There's also ladders and stairs that are going to be going on over the top of this, which allowed the operators to get up over the tender and attend to the rear coupler without getting off the locomotive. But then you might ask, why is there a tender at all? Why isn't it just a tank engine? There is actually a tank engine version of the A3, the A3T, but this version, the A3, is what's called a road switcher. I think this is a classification that might be unique to North American railroads because North American railroads are big, really big. There are yards here that are probably bigger than some short lines in the UK. And in addition, a road switcher had the ability to go out on the main line for short stretches to shunt cars back and forth between exchanges, that sort of thing. So the little bit of extra range afforded by a tender was valuable for a road switcher. Overall, the design for this locomotive was a great set of compromises for North American railroads, and hence why it was so very popular. It was used on many, many railroads, including the variation of it, the U3, which is an 060 version that was used on my beloved Canadian Pacific Railroad around this time. Well, that is the tender water tank. You might be wondering if it's watertight. Probably not. I don't know yet, but it won't matter because I'm going to be sealing the insides of these joints with Honda Bond or JB Weld, something along those lines, because this doesn't have to take heat or pressure, so there's no reason to kill myself to make it watertight on solder alone. I'm not ashamed of that, and I'll be doing that at some point later after coating and everything is done, and then we'll find out how watertight it is. Thank you very much for watching. Thanks to my patrons for making all of this content possible and making it so I don't have to do ads or ad reads or sponsored content. That means a lot to me. I hope you appreciate it as well, and I'll see you next time.